Okay, welcome back again. So in the previous hour, I made an example of duality, and the example showed that we haven't seen this kind of an example before yet, because I skipped a few properties that I should first start with. We will go through those properties first, but before that, I have to make another correction, particularly in this last example that we have seen. The numerator and denominator values, the constant coefficients should be actually 4. So it's 4 divided by 4 plus t squared, because that would be the Fourier transform of e to the minus 2 in magnitude t. And where does it come from? We will see soon. But first we have to correct this because of the formula that corresponds to e to the minus a times magnitude t is actually 2a divided by a squared plus omega squared. So it's we have to use 4 in the numerator and 4 in the denominator. We have to make this kind of a correction first. So in order to see this example, or to have an understanding about this example and some other things that we have seen, let me go through a few more properties that I have skipped unintentionally. There are 3 properties that I have to go through. The first property, which I skipped, oops, so it's red, let's make it black. The first property that I skipped is fortunately an easy property, that is the linearity. And that linearity property is telling me that if x of t has the Fourier transform of x of j omega and y of t has the Fourier transform of y of j omega, then a times x of t plus b times y of t will have a Fourier transform of a times capital X of j omega plus b times capital Y of j omega. Okay, so if you combine 2 time signals, their Fourier transforms are combined. Previously, we had this kind of a property for the Fourier series too, but there was a condition that the 2 signals should have the same period. Now we don't have that kind of thing. It can be just 2 very arbitrary signals with Fourier transforms, and when you combine them, their Fourier transforms are combined. As simple as that. The other thing, which is relatively important, is time shift. What happens to the Fourier transform of a signal when you apply a time shift to that signal? So x of t has a Fourier transform of capital X of j omega. So what is the Fourier transform of x of t minus t0, let's say? In terms of x of j omega, what is that? Again, it's very similar to the Fourier series. It's e to the minus j omega t0, capital X of j omega. So we multiply with a complex exponential. Okay. That is exactly the same thing that we did for the Fourier series. So this is the time shift. Now we can use this linearity and time shift properties all together to come up with one example. You can solve this example in several ways, multiples of ways, but I'm going to show you or mention about a few of those. Suppose that you have this x of t signal, and the signal is as follows. It starts at 1 and goes up to the value of 1 and stays as 1 until time is 2. When t is 2, it jumps up again to 1.5, 1.5, and goes on that way until 3. 3, it comes down to, again, 1. And at 4, it goes back to 0. Everything else is equal to 0. So this is x of t. What is the Fourier transform of this, and how can you find it? You can find in various ways, as I say. For example, you can split this into 3 rectangular boxes. Each of them are differently shifted. One of them is here, the other one is here, and the other one is here, for example. So you can solve it as shifted versions, where you apply this shift property. Shifted versions of a rectangular box around the origin. So they shift by different amounts, and they scale by different amounts. One of them is scaled by 1. The second one is by 1.5, and the third one is again by 1. And then you combine. So you use the linearity property. That is something that you can do. Or an equally easy way of solving this problem could be considering it as a rectangular box like this and another rectangular box which makes this addition. Okay, 2 boxes. One of them is wider than the other one, and their scales are different, and their shifts are the same actually. They are both shifted to around 2.5 from 0. So I will do this way. So I will think of a rectangular box like this first, from minus 0.5 to 0.5 with a magnitude of 1. This will I will call x1 of t, and then I will have another wider box from minus 1.5 to 1.5. Magnitude is again 1, and I'm going to call it x2 of t. And I will shift both of them by 2.5 to the right-hand side. And I will scale x1 by 0.5. I will scale x2 of t by 1. And then I will combine to come up with x of t. So whatever I do for shifting and scaling and combining, etc., I will do the corresponding Fourier transform operations on the Fourier domain. So what we have is this thing will have an x1 of j omega, which is equal to, I'm just cheating from the table here because you will also be enabled with the tables. So you will be able to look at the table to know what the Fourier transform of this one. You don't have to derive the Fourier transform of this one again. And similarly here, x2 of j omega will be equal to 2 sine 3 omega over 2 divided by omega. So what am I gonna do? I will have a half of x1 of j omega and all of x2 of j omega, and then I will apply a shift to it by an amount of 2.5 to come up with the Fourier transform of x of t, which is x of j omega. And this one will be, the shift is simple. It is e to the minus j times 2.5 times omega, okay? And the others are half of the first Fourier transform, which is simply sine omega over 2 over omega, and 2 sine 3 omega over 2 over omega. So I can write it like this. The denominator of omega can be put as a common thing. You can leave it like this, and that would still be full credits. You can try to simplify this expression a little bit, but that would be very unnecessary. So 3 boxes will give you probably a different looking expression, which will be equivalent to this expression, or addition of these 2 wider and narrower boxes with some shifts. It will be this. Both of the equations or both of the outputs will be correct. They have to be evaluated as correct, although they look a little bit different, but you can show that they are equal to one another using mathematical formulas and things like that. So this is one correct solution. It is the correct solution in a sense. All right. Now, the thing to come up with the last example of the previous hour is coming from this property, that is conjugation and symmetry. It's this: if x of t has a Fourier transform of capital X of j omega, difficult to show it. If you conjugate your time signal, its Fourier transform is conjugated altogether, and with a substitution of, instead of j omega, you put minus j omega, or every omega is replaced by minus omega, and it's also conjugated. This is easy to show, really. Just write the formula and inside it put the conjugate term, and then make substitution of variables. You will see that. Now, this conjugation property has some implications. For instance, if x of t is real, then x conjugate t will be equal to x of t. The conjugation of a real signal does not change anything, which is telling me that x of j omega would be equal to x conjugate of minus j omega, which is equivalent to saying x of minus j omega would be equal to x conjugate of j omega. So if you conjugate and then put omega is equal to minus omega, you should be getting the same expression for real signals. This means conjugate symmetry. It's like you have x of j omega and you have x of minus j omega, which is just folded version around the omega axis. Instead of x of omega, you have x of minus omega, in other words, and that is equal to the original one's conjugate. So it is telling me that x of omega, x of j omega, is a symmetric signal for real signals. It is symmetric, but it's conjugate symmetric because it's complex valued. But we have even one further thing about it. If x of t is real and symmetric, so it's also an even signal. In other words, x of t is an even signal. You remember cosine t? What was the Fourier transform of cosine t? It was 2 impulses. So it is a symmetric, cosine is a symmetric signal, and its Fourier transform is real. But if it is antisymmetric like sine, then its Fourier transform will be imaginary. For all others, it will be just complex. So if x of t is real and symmetric, then x of j omega is also real and symmetric. It comes from here. If x of t is real, x of j omega is conjugate symmetric. And if x of t is symmetric, x of j omega is real, like the cosine's Fourier transform is real. Or a rectangular box around the origin, what was its Fourier transform? It was sinc, which is real. So symmetric signals give you real Fourier transforms, and real signals gives you symmetric Fourier transforms. So if it is real and symmetric in time, then it is also real and symmetric in frequency. This is the conjugate and symmetry property, which gives you this kind of a separation. You can split your x of t, we know it, to even parts, even part of x of t, which is symmetric, and odd parts of x of t, which is antisymmetric. And even part of x of t will give you the real part of x of j omega, because if it's an even signal, then its Fourier transform is real, and even part will give you the real part of x of j omega, and the odd part will give you the imaginary part, j times the imaginary part of capital X of j omega. So just like splitting your signal into an even and odd parts, you can split your Fourier transform to real and imaginary parts. And the real part is handling the symmetric part of x of t, and the imaginary part is handling the antisymmetric, the odd part of x of t. Okay, this is also something that may be of use in some cases. So how can we use this? I'm not going to use it as it is first for solving this question, because I should be solving this question at the very beginnings as a second example, but I seem to have forgotten to do that. So now let's do it. But it is also related to this conjugate symmetry property. E to the minus a absolute value t. What is the Fourier transform of it? Let's start by doing it, literally. And how do we do that? By putting it into the Fourier transform formula. Sometimes you have to remember it. E to the minus j omega t dt. This was the formula of the Fourier transform. Now I can split this integral into two parts, where one of them is for t is negative, the other one is for t is positive. Because absolute value of t for t is negative will be minus t, and absolute value of t for t is positive is equal to t. So I'm splitting it into two parts, like one from minus infinity to 0, the negative parts. So that is e to the minus a times minus t, which is e to the at. E to the at, e to the minus j omega t dt. And the other one is from 0 to infinity, the rest, the positive parts, where t is absolute value of t is equal to t, e to the minus a times t times e to the minus j omega t dt. Clearly, you can combine these exponentials into one exponential term, and the integral of an exponential is something that we know. It is 1 over that exponent term, e to the exponential, from 0 to minus infinity, or from infinity to 0. And when you do that, one of them, this one, the answer you already know, because that corresponds to e to the at u of t, is Fourier transform. And what was it? Let me write it if you wish. It was 1 over a plus j omega, this one. The other one, when you do the same algebra, you will find it as 1 over a minus j omega. So their summation is equal to 1 over a minus j omega plus 1 over a plus j omega. And when you do that by equating the denominators, multiply the first term by a plus j omega, and that will give you a plus j omega in the numerator from the first part, a minus j omega for the second numerator. J omegas will cancel, and you will have 2a. And since the denominators are conjugates of one another, the denominator is quite simply equal to a square plus omega square. Okay, this is the Fourier transform of e to the minus a t. Okay, this is the formula. Of course, this is for a greater than 0. Yeah, I forgot to mention about that. If a is greater than 0, then e to the minus a absolute value of t will be a decaying exponential in both sides, like this. Okay, from both ends, it will decay. If a is negative, then e to the minus a absolute value of t will go and diverge, like this. This is for a less than 0, and this one is for a greater than 0. So a must be greater than 0 so that the Fourier transform integral converges. Otherwise, you will have a divergent integral, and it's not going to work. The Fourier transform for that does not exist. It violates the so-called Dirichlet conditions, the conditions for the Fourier transform to exist. It mustn't diverge. So this is the formula, and that's what I used in the first, in the, sorry, it was in the same page, sorry, up here a little bit. Yeah, here, in this example, the example where I'm looking for the Fourier transform. So I was using it in the form of 2a divided by a squared plus omega squared, which is the Fourier transform of e to the minus a absolute value of t. And here a is equal to 2, okay, for this example. It was that way in that example. So let me come back now to this. And I want to think of it in the following way. E to the minus a absolute value of t is equal to actually twice the even part of e to the minus atu of t. What was e to the minus atu of t? It was half sided, like this, right? This was e to the minus atu of t, with this thing being 1. What is the even part of a signal? How do you find the even part of a signal? An even part of x of t is equal to x of t plus x of minus t over 2. That's simple. You have x of t itself, its flipped around version, x of minus t, you add them up and you divide by 2. That will give you the even part. So what is the even part of this shape then? This half-sided exponential decay? You fold it around, it will be decaying at both sides. And then you divide by 2, so it will be 1 over 2. Starting point will be 1 over 2 and decaying exponentials. But e to the minus a absolute value t was this shape, starting from 1. If you take the even part, it starts from 1 over 2, so you have to double it. That's why it's equal to 2 times the even part. So if e to the minus a t is twice the even part of this, let me write it again, then the Fourier transform of it, which is, let's say, x of j omega, must be equal to twice the real part of the Fourier transform. Twice the real part of Fourier transform of e to the minus atu of t. Okay, the real part of the Fourier transform of e to the minus at u of t. What is the Fourier transform of e to the minus at u of t? It was 1 over a plus j omega, right? It was 1 over a plus j omega. That was the first example that we did. I remember that. So what is the real part of it? Real part of it. And I have to multiply that real part of it by 2. How do we find the real part? If it is in the denominator, it's difficult to find the real part. So we have to multiply the numerator and the denominator by the conjugate of it. Twice the real part of a minus j omega divided by a plus j omega times a minus j omega. Okay. And it is therefore twice the real part of a minus j omega divided by a squared plus omega squared. Okay. And the real part only takes or picks this one, a. So it is 2 times a divided by a squared plus omega squared, which is 2a divided by a squared plus omega squared. Now look at this boxed thing and this one. They are the same. Okay, we could find, therefore, the Fourier transform of e to the minus a absolute value of t by taking the real part of the Fourier transform of e to the minus at u of t and multiplying by 2. It will give you, again, the same thing. So this was an example that I seem to have skipped before the previous, but it's there anyway. Now comes the last property, which is again a property that we have seen from the Fourier series, continuous time Fourier series, that is the Parseval's relation. Which relates the energy of the signal in time and in frequency. What is the total energy of a signal? It's this, x of t magnitude squared dt, the area under magnitude squared time signal. This is the energy, and the same thing is valid in the Fourier domain as well, but only with within a scaling factor of 2 pi. So you find the energy of the Fourier transform signal, magnitude squared d omega. How are we going to use this? You can use it for finding, for example, the energy of a sync signal, which would be very difficult, right? Because sync is sine pi x over pi x. And when you take the square of it, it would be mass. And when you integrate it, you have to consult your calculus books for the integral formulas. Even there, you may be having difficulty in finding the integral. So you don't want to evaluate the energy in the sync domain, sync signal domain. Go to the other domain. The other signal domain will be rectangular box shape, and the energy of a rectangular box shape is the box shape magnitude squared, which is again another box shape, and find the area under the box is a piece of cake. Okay, that would be quite an easy process. So whichever domain is easier for you for evaluating the energy, evaluate the energy of the signal in that domain. That is the trick. Now, although I said this is the last property that I want to mention about, I will denote this thing as a property, convolution property. But it shouldn't be listed inside the property. It is so fundamental that it must have its own unique section name, not like any other property, but this is a significant thing which deserves a section. The thing is, I will first write the property. If you have x of t, and if you're convolving it with h of t, suppose that x of t is the input to a linear and time invariant signal system, and h of t is the impulse response of the system. So how do you determine the output? The output is y of t is equal to x of t convolution with h of t. Or it may be just any convolution that I request as an exam question. I want you to convolve these two signals. Now, if you can take the Fourier transforms of those two signals, x of t and h of t, then you can obtain the Fourier transform of the output way easier. It's like this, x of j omega times h of j omega is equal to y of j omega. So in the Fourier domain, you just multiply the Fourier transforms. You don't convolve them in the frequency domain. And I believe multiplication is easier, right? Convolution is a complicated or cumbersome operation. You flip around one of the signals and slide over the other one, make a multiplication, find the area under the multiplication term, and then continue sliding and evaluating. You know how to do convolution. It's certainly not multiplication, but when you take the Fourier transforms of individual signals, you simply multiply them. And that is an amazing way of doing things. There are multiple ways of proving this property. Convolution in time versus multiplication in frequency. We have seen this as, or let me do that. We have time. I will just give you two alternative ways of motivating or proving this property. And after that, we can just stop the lecture and wait for the Wednesday lectures. We know that e to the j omega t, so this is proof, proof 1, you can think of it. E to the j omega t going into a system with impulse response h of t would give you h of j omega times e to the j omega t. This is something that I explained to you during the Fourier series. And I said that if you combine the left-hand side of exponential terms, if you scale them and combine them, you have to scale and combine the right-hand side terms too. So every Fourier series coefficient ak is therefore multiplied by h of j omega at omega is equal to k times omega 0 or omega k. But actually, it's also valid for all kinds of combinations. So if the left-hand side gives you right-hand side as the output, which I have proved before by just convolving e to the j omega t with h of t, I did that. I remember it. Just check your notes or videos. You will find the proof of this expression. And now that you have this expression, let me write it again, but like this. I will leave some emptiness, like this, h of j omega e to the j omega t. So I'm leaving some places empty because I'm gonna fill them. For instance, e to the j omega t, I will multiply by x of j omega. It's just a term. And that is a term in frequency, so that it's not a time term. Therefore, it's a scale. If I scale the input, the output will be scaled with the same. Okay. And then I will integrate this and integrate this similarly. Okay. And then I will put a 1 over 2 pi term here and a 1 over 2 pi term here. And the thing that I have at the right-hand side, I already know that the right-hand side is equal to y of t. That's by definition. If I convolve it with, if I convolve h of t with x of t. And look at the left-hand side equation now. Left-hand side of the system, the input signal. The input signal is the inverse Fourier transform of x of j omega, capital X of j omega. Therefore, it's x of t. Do you see that the left input signal is x of t, isn't it? It's x of t going into h of t, so the output is y of t. Okay. Meanwhile, it's equal to the inverse Fourier transform of y of j omega. And what is that y of j omega? That y of j omega is here. Because in that formula of 1 over 2 pi something, integral something times e to the j omega t dt, that something must be the Fourier transform of your signal. The Fourier transform of y of t is y of j omega. Therefore, y of j omega must be equal to x of j omega times h of j omega, which was the thing that we were trying to prove. Y of t is x of t convolution h of t. Y of j omega is x of j omega times h of j omega. And we can see it from this input-output relation. That is a way to prove it. There is another way to prove it. Proof 2, let's say. And I will start from the end this time. I will say that y of t is equal to, or let me put it like this. Y of t has the Fourier transform of y of j omega, and that y of t is equal to the convolution of x of t and h of t, whose formula I can write from minus infinity to infinity, x of tau, h of t minus tau, d tau. Did you think that we are going to forget the convolution formula? No, we must always remember everything from the beginning of the course until wherever we are left. So y of j omega is the Fourier transform of it. The Fourier transform of y of t is equal to the Fourier transform integral which is from minus infinity to infinity. And inside it, I have to write y of t. And y of t is integral from minus infinity to infinity x of tau, h of t minus tau, d tau. This is y of t. And then I take the Fourier transform times e to the minus j omega t dt. This is the convolution. This is y of t. And the whole thing is the Fourier transform. Okay. Now that thing is equal to, we have a few integrals. D tau is somewhere and dt is somewhere. So let's try to interchange the places in such a way that or the outmost integral will be related to tau. So y of j omega is the thing that I'm looking for still. Integral from minus infinity to infinity, I will isolate x of tau here. And I will put d tau at the end. But inside it, there is something that is related to t, or an integral of t. So that is integral from minus infinity to plus infinity, h of t minus tau. And there is also e to the minus j omega t. So both of these terms, h of t minus tau and e to the minus j omega t, have t inside them. So they must remain inside the integral of dt and then d tau. Since integration is a linear operator, I can interchange the orders of integration over t and over tau. And that's what I did. Now, t is from minus infinity to plus infinity, okay? So what is t minus tau ranging from in that case? Or let me make this kind of a change of variables. I will say here t minus tau will be, let's say, t prime. If t minus tau is t prime, then t is equal to t prime plus tau. And that makes the integral, again from minus infinity to infinity, but h of t prime e to the minus j omega t prime plus tau dt prime. And that is, I'm just focusing into this integral, okay? In the green print, I'm only taking a look at the inside integral. And that is integral from minus infinity to infinity, h of t prime e to the minus j omega t prime e to the minus j omega tau dt prime. Now this term has nothing to do with t prime and can be taken out of the integral. So everything becomes e to the minus j omega tau. What is left? It is h of t prime and e to the minus j omega t prime dt prime. What is it? It's the Fourier transform of h. So I'm going to write it. Let me write in green. It is this times h of capital H of j omega. It is the Fourier transform of h of t prime or h of t. T prime is just a parameter. So I will substitute all of this back into here and say that this is equal to, therefore, from minus infinity to infinity, x of tau e to the minus j omega tau h of j omega d tau. Okay, and then I will move this to the out of the integral because it has nothing to do with tau. H of j omega times integral from minus infinity to infinity x of tau e to the minus j omega tau d tau. And what you see here is the Fourier transform of x, or x of tau, which is capital X of j omega. So in short, this becomes h of j omega times x of j omega. And what was it in the beginning? It was y of j omega. Wow, it was long, but we did it, we proved it. Clearly, you won't be responsible for the proofs, but understanding the idea or having some understanding regarding how to manipulate things to solve problems, to show something that is, whatever it is. H of j omega is it frequency response? Doğukan asks. Yes, of course, that is called the frequency response of the filter H. But I have shown it from a perspective of an input signal and a system with an impulse response h of t, because that's where we require convolution. But mathematically speaking, if you have two signals, x of t and y of t, and if you are convolving x of t and y of t in time domain, the Fourier transforms of those can be multiplied, whether it is a system with frequency response in the notation of H or not. What I'm saying is x of t convolution with y of t, Fourier transform is capital X of j omega times y of j omega. That's what I'm saying. Of course, the way to look at it from the perspective of systems will help, because it is where we are doing convolution. That's how I have proven this property, which is an important property and requires its own thing. It's not own section, okay? It deserves a section. Where can we use it? We can use it for filtering, as your friend has suggested. It's a frequency response. Therefore, we can use it for observing filtering. Suppose that x of j omega is a signal like this, okay, where this part is a high frequency, let's say W2, let's say, from minus W2 to plus W2 on the frequency axis. This is your signal. And it passes through a system whose frequency response is a low pass filter, like this, from minus W1 to W2. So it limits the frequency range. This is H of j omega. So if x of t goes into this system, H of t, what is y of t? Y of t is the, we multiply x of j omega and H of j omega to determine y of j omega, which limits everything into this range. So it is cutting the overshooting parts from minus W1 to W1 is retained, and anything beyond W1 is gone. So y of j omega is this, and you say that y of t is equal to the inverse Fourier transform of y of j omega. If it is a known expression, mathematical expression, you can just take the inverse Fourier transform. Otherwise, you can just leave it as it is. You can use computers to evaluate the Fourier transforms and the inverse Fourier transform. You have this shape, you can put this signal into a computer and ask for what is the inverse Fourier transform. The computer will tell you what it is, and the output is therefore this way. It is found this way. You multiply in the frequency domain. And this is a low pass filter, this H of j omega. It's a low pass filter. It could be a band pass filter, high pass filter, and all sorts of filters are available to you. A derivative filter, let's talk finally about it. What was a derivative filter? If x of t goes into a derivative filter, the output is d by dt x of t. What is the Fourier transform of d by dt x of t? It is, we just did it last hour, j omega times x of j omega. So j omega, this thing, is therefore h of j omega. The frequency response of a derivative filter is j omega. Let's plot it. Plot the magnitude of it, h of j omega. The magnitude of j omega is absolute value of omega, which is like this. Okay, a 45 degrees split like this shape. What is this? How can you describe this filter? So a derivative filter is a filter. It's a linear and time invariant filter. And how can you describe this filter? Is a verbal expression. So you have to give me or tell me, like, is it a low pass filter, band pass filter, high pass filter, band reject filter, whatever, something like that. Do you have any suggestions for that? Can you give a name? It can't be considered as any of these very rigorously, but can you say that, for instance, it is a low pass filter? Is it a low pass filter? I'm asking for a yes or no answer from you. No, yeah, as low can, yeah, and Fatma, I cannot sometimes decode your nicknames. FTMZYRK. Okay. Yeah, the answer is no. It's certainly not a low pass filter. It's not actually, as you see, passing the DC. It is passing more, it's amplifying more as the frequency goes higher. As the frequency goes this way, its amplification intensifies. So it's actually a high pass filter. It's a very high pass filter. So I can say that sort of high pass filter. But it's only rejecting the DC. The other lower frequencies are suppressed, attenuated, and as the frequency increases, it is passing more and more and more. It's not an ideal high-pass filter. An ideal high-pass filter will have a reject of 0 for some low frequencies and a passing amplitude of 1 at the tail portions. It's not like that, but this is a high-pass behavior that it has. So a derivative filter shows a high-pass behavior. It is important, for example, in image processing, because in order to detect edges, which are high frequency contents, you have to apply a derivative filter horizontally and vertically in 2 dimensions. That is image processing, by the way. Okay, so this is the relation between convolution in time and multiplication in frequency, and please be aware of these. We can now stop at this point. We will continue on Wednesday. If you have any questions, I'm gonna give you like 10 seconds or something to tell me about it. Or yes.
Hocam ben bir soru soracağım da belki Fourier serileriyle alakalıdır. Aklıma şöyle bir şey geldi. Acaba böyle periyodik bir kare sinyalimiz varken bunu low pass filtreden geçirirsek sinusoid bir sinyal alabilir miyiz?
Exactly. So the question, let me translate because it's still in the recording phase. If you have a periodic rectangular pulse train, when we low pass filter it, can we get a periodic sine wave? That is exactly what they do in the power generating plants. The hydroelectric power dams or any kind of power generation is usually something rotating, and that rotation is sometimes on and sometimes off, and it normally generates a rectangular voltage waveform, up and down, because it touches and it does not touch, and touches and does not touch. In order to convert it into a pure sinusoid that we use at our home appliances and mains and plugs and things like that, it becomes a sinusoid by low pass filtering. Exactly. If you can pass only the first harmonic, and if you can stop all the other harmonics, for a rectangular square wave, half duty cycle square wave, by the way, you may remember that there is a fundamental frequency, omega 0, and the other harmonics are at 3 omega 0, 5 omega 0, 7 omega 0, etc. If you can just put somewhere after omega 0 and apply a low pass filter, you will only have 2 impulses in the Fourier domain. The other impulses of the other harmonics, they will be chopped off. You will have only 2 impulses. And what is the time domain signal corresponding to 2 impulses in the Fourier domain? It's a cosine, it's a sine wave. That's exactly what you're supposed to do to generate a sine wave.
Hocam o zaman filtrenin katofunu şeye göre mi ayarlamak lazım? Birinci harmoniye göre mi ayarlamak?
Yes, you have to just put a cutoff which includes the first harmonic and does not include anything else. You have to adjust the cutoff frequency, of course.
Aydınlandım, teşekkürler.
All right, that is how they do it in power generation. Okay. All right, any other questions? All right, you may think of other questions meanwhile until Wednesday. So I'm stopping the recording now, and Let's meet next Wednesday.